Welcome back to the lab, welcome back to EE for everyone. Today we're going to discuss how I considered modularity in our motor controller design. This design is an example of a modular system, but these considerations should apply to nearly every modular system. If you're designing something that connects to something else, or you plan to, well, I'm sure that you can learn what not to do by watching the rest of this video. We're going to discuss some limits, parasitic elements, and potential compatibility issues that might arise in our system. We're also going to discuss how the physical connector choice is important because it impacts the rest of our system. This is going to be a lot of fun, so let's dive in. Modular systems, especially one like this motor controller, is easy to underestimate. You might look at any one piece and it seems crazy simple. A microcontroller, a power supply, and a motor driver. And that's it! It should only take 10 minutes to capture the schematic once the symbols are created. It's just not that difficult. However, rushing through the details of how these modules will interact can lead to some pretty crippling problems, so let's talk about that. Let's start with common impedance coupling. This can occur on a cable, on a PCB, this can happen anywhere. In this system, I want to daisy chain power for the logic, communications, and processing circuits. To overstate the obvious, that means that power will come from somewhere and flow through a cable from each module to the next. And that's great because we won't need 10 power supplies to control 10 motors, but what is not so great is that cable will introduce its non-ideal effects into our system. Common impedance coupling, which comes from resistive losses, is one of those effects. Let's say that we end up with a chain of 10 modules, and that last module is using a relative lot of power. Let's pretend that power is intermittent, as in not a constant current load. Even though there's only one module that's consuming power in this scenario, the current going to it needs to flow through all of those cables, connectors, and circuit boards on its way to the destination. That current contains DC elements and AC elements, and that has mixed frequency content. Hold that thought while we consider this cable and its parasitic effects in more detail. The cable that I hope to use is as cheap as it comes. 4 parallel conductors, unshielded wires, and an external jacket. This is commonly referred to as phone cable because it's used a lot in telephone systems. We'll be using some ribbon cable as a stand-in today because mine is in the mail. Ignoring external interference for a moment, let's consider the potential coupling modes for noise to move from one wire to the next on this cable. More generally, what even is a cable? In theory, it's a group of perfect conductors with no resistance, capacitance, or inductance. In reality, this system has an imperfect set of conductors that exhibits resistance, capacitance, and inductance. We already know that in order for there to be interference from one conductor to the next or one system to another, we need a noise source and a coupling mode. The coupling modes primarily come from inductance and capacitance, so let's model these inductances and capacitances with a few measurements on our LCR meter. We'll get to the noise in a second. Sometimes I feel like there is someone special looking out for me in the world, and today is no exception. Like, as of days ago, one of you commented on our last video that showed the DE5000 and reminded me to calibrate the meter every time I change probes. All I can say is, you da man, or da woman. I hope I can dig up your comment to feature it here, and my apologies if I can't. Sometimes it's hard to find comments again, but regardless, you know who you are, and I just want to say thank you. That's a great reminder and a very timely one, because the capacitances and inductances we need to measure today will be extremely small. If there's some stray capacitance or inductance in our probes, that's going to be a problem, because the capacitance in our probe might be as much as the capacitance of the cable. So we're going to calibrate this first with doing the self-cal with the meter open and shorted, and then it's time to take some measurements. Power on the LCR meter, and we need to perform a calibration. Give it 30 seconds to do the open cal. Cal is complete. Tap cal again. Now we're doing the short. Hold the probes so that they're shorted together. Press it again. Hold for 30 seconds. As this is calibrating, let's talk a little bit about what we're expecting. Let's start with capacitance, and assuming these conductors operate as a parallel plate capacitor. I want to estimate the capacitance that we're going to measure before we measure them, because it's difficult to know if your measurement is in a realm of reasonable or not. And if our measurements aren't reasonable, that means that our meter probably isn't the right meter for this job, as in we need a higher precision one. So we're going to use a parallel plate capacitor, though I know it won't be perfect, just using the plate area of the cross-sectional area of one wire to the next and the spacing from center to center, conductor to conductor. That's not really how this is going to work. We have round conductors. The field lines are not just going to be going straight from one to the next. There's probably a better model here, but this will be close enough. We're about to take the real measurement. Moving on. I'm also assuming a relative permittivity of 1.5, and I expect the capacitance from wire 1 to 2 at around 1 picofarad. That's about what I'm expecting. Because of this assumption of the parallel plate capacitor, we'll expect that to halve from wire 1 to 3, or be 1/4, a quarter of a picofarad from wire 1 to 4. Okay, so let's start with our first measurement. We're going to measure the capacitance from one conductor to an adjacent conductor. That should be these two pins, and 12 picofarads. Let's grab a different adjacent pair. We would expect to get about 12 picofarads as well. For a different pair, this should be about 12 as well. And now we might be introducing some error because there's some twistiness, there's some crossing over, but we are getting approximately 12. We can take the average of that. It looks like we're pretty close to 11 picofarads. Now we want to measure gaps that are 2 conductors wide. So I'm looking at the purple and the green. I'm seeing, how is that, 7? 7.4. 7.4, that is fine. Here's another one, so it should be about the same. We should get 7.4. Getting 8. Let's call that 7.7, thereabouts. The final one, we can only measure this once with this cable construction. We're going all the way from the outer pairs. We're going green to gray. We should see a rough halving as well. Not quite. We're seeing 6.4, 6.2, 6.3. This is all at 10 kilohertz. As I measure the capacitance, we observed 11 picofarads, 7.7 picofarads, and 6 picofarads, respectively. This tells me that one or all of the assumptions we just made were not correct. It's possible that the relative permittivity is greater than 1.5, where the real scenario is just more complicated than a parallel plate capacitor. There's extra conductors in here. There is a lot going on. It's also possible that this LCR meter isn't accurate enough to reliably measure the situation. That all said, it could be one or all of these factors contributing to the difference in what I expected and what I measured, but let's just assume our measurement is more accurate than our expectations and move on, because we have some inductance to measure as well. The way that we intend to use this cable, there are 2 primary inductive loops. There's an outer loop that will be carrying power and an inner loop which carries the differential RS-45 signaling. These loops need to be considered because electrons will flow in and out of the ground and power conductors in a loop, and that can induce a current in the RS-45 wires, and that could be differential noise. That inner loop might not seem like a loop at first, but it's the termination resistors on either end of an RS-45 network that will allow current to flow, inducing some voltage. Hopefully, this graphic is helping you to visualize, because it's not intuitive until you stare at it for a while. You can probably guess where I'm going with this. There are 2 major inductances that I'm worried about. There's the self-inductance, which can lead to transient over and under voltage events as the load changes, and there's the self-inductance of each of these loops, which is more important for the power conductor because that can lead to transient over voltages and under voltages if there's not enough capacitance around the bus. The other inductance that can be really sneaky is the mutual inductance between the power and ground pairs. So as we're investigating inductance, there are a couple things that I need to do. First of all, we need to assemble our inductors. So I'm going to short the outer conductors together, which will make an outer loop. So now we have a rectangular loop going around the outside of this cable. And then I will short the inner loop, which is now shorted. So now we have two loops of cable. And let's measure the inductance. So we'll want to make sure this is in series inductor mode as we measure it. But let's do the outer loop first. We want green and gray. And that's what we're clamped on. You can see it didn't grab the right mode, but we're measuring such small values. It's assuming we want to measure the resistance. Let's bump that over to inductance. And the outer loop is measuring, we are measuring 0.47 microhenries. That's pretty close to what we expect. And now let's measure the inner pair. We'll call it 0.3. In general, it seems like my assumptions around inductance were a lot more accurate because my expectations were closer to reality. I measured 0.47 microhenries for the outer loop and 0.3 microhenries for the inner loop. Considering the coupling factor equation, where K is the coupling factor, if we're measuring the inductance of both loops we just put in series, we will learn two things. I'm connecting these coils in such a way that I expect them to be added in series. So if there's no mutual inductance, we'll measure the sum of these self-inductances, or 0.77 microhenries. If the total inductance is greater than 0.77 microhenries, that means there is a mutual inductance, and I've connected the coils in series correctly. If the total inductance is less than 0.77 microhenries, that means I got the polarity backwards, but there's still mutual inductance. Combined, this will give us the coupling coefficient and the relative polarity from one coil to the next. And now this is where it gets fun. I printed this off because we don't just care about the inductance. That matters, but we care about more than just the inductance. We care about the coupling, and we care about whether it's coupled in reverse or in a positive direction. We'll cover that in a second. So we're about to learn a couple things. We're going to learn what the K coupling factor, which we can use in like LTspice, etc. But to do that, we need to know what the mutual capacitance is. Sorry, the mutual inductance. We need to know what the mutual inductance is. And to measure the mutual inductance, we're going to measure the total inductance when we add these in what we think is series. And we'll realize if they're wound in a direction where the dots are facing the same way. So that is, if the polarity is positive conceptually, going around the outer loop and then around the inner loop in the same direction, or if for some reason that ends up getting flipped on its head and it goes around in one direction and around in the opposite direction, we will figure that out if our inductance is above or below the sum of our two inductances. So if we get a total inductance measured of 0.77 microhenries, that'll mean that we have a mutual inductance of 0. So let's measure this. Let's see what direction the dots are facing. And let's fill out this table as we go so I don't forget what we're doing. We have 0.47. This is outer. And we have 0.3 inner. And that makes sense because the inner loop is physically smaller. So we would expect a smaller inductance. Now, we will connect it so it goes around. Okay, so it goes around and then around again. And I twisted this so we can short green to gray to blue to purple. So I'm going to short blue and gray together, and then we'll measure from green to purple. And so if we get a number that is larger than 0.77 microhenries, we will then know that they are wound with the dots in the positive direction. That looks like the number, 0.94. Okay, very solid number, 0.94. So with that in mind, 2m becomes 0.77 minus 0.94. Divide that by 2, and I'll have to duplicate this with the real cable, but this will get us in the ballpark. We are at about 0.085 microhenries. Using our equation then, our coupling factor is 0.226. Okay, 0.226 is our coupling factor. What does that mean? That means that if we have AC current, keep in mind this is AC current, that is going in the one outer conductor and coming out the other conductor, not DC current, but AC current that is doing that, then in the same direction, so that is if it's coming in the gray conductor and out the green conductor, we can expect the purple conductor to be slightly higher and the blue conductor to be slightly lower than the potential we were expecting. I measured a total inductance of 0.94 microhenries, which leads us to a mutual inductance of 0.085 microhenries and a coupling factor of 0.226. Well, now that we have an approximate value for the dominant and parasitic elements for 1 foot of this cable, let's bring this information into LTspice, let's model this cable and simulate how this cable may behave in a system. What you're seeing now is my capture of exactly that. You can see some parasitic resistance, capacitance, series, and mutual inductance. As I'm looking at this again, as I'm editing this down, I'm questioning how I modeled the distant conductor capacitance. When measuring from conductor 1 to 3, the 11 picofarad capacitors are in series, which would effectively half their value, leaving 5.5 picofarads. If I look at what I'm expecting to measure for the other 2 conductors, we're only expecting to measure 7.7 picofarads from conductor 1 to 3, which means I should add an additional 2.2 picofarads in parallel with that 5.5 picofarads. As in, I should change the value of C5 from 7.7 to 2.2. I'm not certain that the way that I've captured this is wrong, but I'm also not convinced it's right. So just keep in mind that I may have too much capacitance modeled, and I'll digress for now. Let's add a 12-volt source, RS-45 transceiver, and termination resistors. This is all assuming that our cable model is correct for 1 foot of cable, and we're going to add a 1 amp load that is modulated at 1 kilohertz on the other end of that cable. This is a pretty extreme example, but let's just roll with it for now. It's clear to see that the voltage received near V4 has some ringing, though I'll admit that no capacitance near V4 is a crazy assumption. Let's add 10 microfarads of capacitance near the load. This reduces the amplitude of overshoot and lengthens the duration of the ringing. While the impact on power can be handled many ways through regulation or filtering at each module, there is a limit to how much we can actually filter the RS-45 lines without corrupting the data. I'm not too concerned about common mode noise. That's kind of baked into the RS-45 protocol, rejecting that, but differential mode noise can lead to issues like invalid logic states, and that is possible, special thanks to our coupled inductors. It's easy to see that some differential noise is coupling onto the data lines here, though the magnitude is admittedly small. I have to admit that at 1 amp, 1 kilohertz load is more dynamic current than I expect to see in the system. Also, the few millivolts of noise is not going to cause any real problems, so naturally, we need to make this situation worse so I have something to worry about. So what if we increase the length of this cable from 1 foot to 5 feet? To do this, we'll need to copy the parasitic components 5 times. I want to consider 2 scenarios, the RS-45 receiver being in the middle of the chain, near 2 feet, and the receiver being at the end of this chain, near the distant termination resistor. Measuring near the end of the cable, the impact is clear. The resistive loss leads to significant voltage drops. Measuring from both ends of this cable shows about an additional volt of drop around that loop at 1 amp. Not ideal. The differential signal near the noise source shows measurable disturbance as well, though this is only 28 millivolts peak to peak. Moving this noise measurement to the middle of the cable, peak to peak noise was about 10 millivolts. I don't have any concerns about corrupting RS-485 traffic with this in mind, but still, it's good to know the relative magnitude of noise we might expect. Quiz question. Does anyone remember why we started talking about this? That's right. Common impedance coupling, and more generally, how the cable parasitic circuit elements will influence our system. I hope that you enjoyed that diversion, but it's time to move on. We have a lot more to talk about. I want to consider two modes of failure that really kind of bothered me as I was imagining how this system might be used. Depending on your perspective, these failures are either certain or unlikely. One of these failures is a short circuit from the motor voltage to a microcontroller pin, finding its way back to the 12-volt rail. Let me explain. Almost every integrated circuit with pins will behave in a particular way. There is almost always a pair of steering diodes from each pin to the positive voltage and to ground. This protects the part if an over/under voltage or ESD event occurs, and it's important. However, the reality is you should never count on using this diode in your design because it doesn't come with rated characteristics. However, the reality is it's very probable that in this fault condition, the motor voltage could end up flowing through this diode. So let's continue. If there's a short of the motor voltage to an I/O pin in the motor driver, internal, it's on the same silicon die, in theory, it could happen. Now that could get into the microcontroller, and then you have some higher voltage, let's call it 30 volts, that's applied to your microcontroller pin. Well, there's that diode, and all of a sudden you're pulling up your 5-volt rail to 30 volts. Well, now that 5-volt rail is pretty closely coupled, and you can easily pass current backward through an LDO, depending on what type of LDO you have, and eventually that could lead 30 volts to our vaguely 12-volt power bus. Taking that a step further, that 12-volt power bus is shared by every module. So if the LDO can't handle your maximum motor voltage, this could be a pretty nasty fault condition. You could end up destroying every motor driver on the bus as well as the controller that's trying to communicate here. Now, that's not what I would call ideal. Well, what can we do about this? Let's start at the source. That motor driver could require multiple amps at around 30 volts. That is a lot of power compared to the about 5 volts and a few milliamps that we'll be consuming in the microcontroller. Even if we put a fuse on that 30 volt input, I'm just not convinced that will be helpful at protecting the downstream digital circuitry. We're going to need to find another way. One thing that could help this situation would be to place a Zener diode or TVS to clamp over voltage on the 12-volt rail at each module. Combined with a fuse or PTC, this can be a very effective way to protect a module, so long as that transient protection diode can pass enough current. A series impedance that will limit that fault current, and a diode that is shunting energy leads to a maximum predictable voltage for a downstream load. You might still destroy the one where that fault occurred, but at least the rest of the system should be protected. Speaking of, adding multiple of this circuit, right, multiple of these transient protectors in parallel, as we would be by connecting multiple modules, will make the system even more resilient since all of those TVS diodes will be put in parallel, sharing the fault current. Now, this won't be perfect protection. There are still faults that could get through, and maybe adding a diode in series to prevent backdriving the power input, maybe that's another way that we can handle this, but I want to bring up this fault condition generally, and you should probably consider stuff like this if you're designing a modular system as well. This fault is more of a problem, and it's an inherent trade-off of RS-485. There's no isolation from one module to the next, like with an Ethernet system, but RS-485 is simpler and cheaper because you don't need a bunch of transformers. It might not seem obvious on the surface, but choosing RS-485 as a communication protocol will likely limit the maximum scale of this motor control system, because the bigger it gets, the more and more likely these types of faults become. As a practical matter, Spreading motors hundreds or thousands of feet apart and linking hundreds of modules together probably isn't something that we need to consider right now. And if we do need to scale the system up, my guess is that we will have an opportunity to mix multiple communication methods, like an Ethernet system for long distance, higher latency, and a shorter distance local communication version as well. We've seen it done before. We could do that too. The second fault I want to consider is a little bit simpler. Let's say someone just makes a cable incorrectly. Let's say that this leads to applying a reverse voltage to a module with pins 1 and 4 swapped on this cable. Power becomes ground and ground becomes power. This would apply a negative voltage to one or more motor controllers. And reverse voltage is a tricky situation to handle. We want a really low impedance in one direction and a really high impedance in the other. Let's think about how we could use that diode and series impedance combination to limit the fault current and how this might impact other systems on the bus and whatever's providing the power. Keeping on that same thought with the fuses and the diodes, adding a second diode, this one, which is just a traditional diode, that can clamp the maximum reverse voltage, and a series fuse or PTC that will either blow or limit the peak fault current. Now that could be a very effective strategy. This can allow the rest of our bus to stay alive, though with a bit more current draw on the 12-volt rail than one might expect. I don't want to get too much into the details here because that diversion into parasitic cable elements ate up a lot of our time together. Let's say this circuit ends up looking something like this. It pains me to say it, but I have this sneaking suspicion like our time is coming to a close for today. On your way out the door, I want to leave you with a couple thoughts. The physical interface or connector in a system like this can become the greatest benefit or most obvious limitation. I'm not sure exactly where this project is going, but I do know that if this module is compatible with existing Modbus equipment, that would be pretty nice. Unfortunately, I didn't pick a connector that leads to that. Why? First of all, because I didn't like the ones that I found, but also because I wanted to distribute power along with Modbus communications, and I didn't see a connector standard combo that really did that, so we'll make our own. On top of that, though, not just wanting to pick something that's already used, I also want to pick something that is universal, cheap, and never going away. Ideally, I'd like to be compatible with off-the-shelf cables that you can already buy, and that's a tall ask. To want something that's already used for Modbus that I can inject power that you can buy off the shelf and that will be around for a long time, well, that's why I picked the 6P4C modular jack. That is 6 positions, 4 populated. It just really stood out to me. If it turns out that we need some extra signals to make the system work, we can add 1 more differential pair or 2 more independent signals onto the cable. That will ensure full duplex or some extra control signals can be supported, if desired. One problem that we haven't really been able to explore yet is synchronizing multiple motors. I want to be able to touch and feel the impact of sending commands in series to multiple motors, and it might not be that noticeable, or it might be the worst idea I've ever had. One potential way we can fix this will be to have some form of a clock pulse being shared by each module, where each module can receive its command and then adjust its position synchronized to the clock. That way we could perhaps receive commands in sequence, like in a series, and execute them in parallel. For example, if we can find a way to give each module its next command while the previous one executes, right, we'll have some time while it's doing that wave shaping and the motor's physically moving. If we can utilize that time to shift in the next command, then it could execute immediately after the previous one is done, totally minimizing the delay between different motors moving, right? Tell them all to move, shift in all your commands, and then tell them all to move again. That could be really cool. It's easy to make a design far too complicated in the spirit of future-proofing, to the point that future-proofing has become a bit of a running joke in the engineering world. To wrap up this story, the 2 spare pins are just enough to make me feel comfortable about some future needs that I could see, without getting too nervous about adding a bunch of extra stuff I don't need. Adding a 30-pin connector probably isn't a good choice. I think we touched on a couple really neat concepts today, and I hope that you enjoyed hearing some of what I considered while building this modular motor system. Coming up next, we'll be discussing why buying electronics components in 2022 is terrible, and planar assembly method for these boards. I'm really excited for the next step of this project, and I hope you are too. Most of all, I hope that you learned something great today, and I hope to see you again soon. As always, I want to give a special thank you to our channel members on Patreon and YouTube. I really appreciate the extra step you've taken to support us directly. I'd also like to thank you for all your support through viewership, comments, sharing what we do with others, those who choose to watch ads, and those who are subscribed. It has been awesome and humbling to watch this EE for Everyone community grow, and that just can't happen without you. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone. Thank you for staying till the end. Bye.